Hey everybody, I'm Elliot.
I'm Liza.
I'm Nicholas.
This is Emre.
And this is our ECE496 Capstone project, the walking Acrobot. So what is an Acrobot? By definition, it's simply two links activated by a single joint, enabling it to perform locomotion, or in our case, walking.
As ECE students, this project posed a significant challenge, as it required considerations of a mechanical, electrical, and control systems engineer. Mechanically, we had to design, 3D print, assemble, and iterate on every single one of these components. Additionally, we had to consider how the electrical components and electrical hardware would actually fit onto it. In terms of the electrical considerations, we had to first determine a sufficient power supply and how to distribute the power. We had to determine the transient behavior of some of our components. And then we actually had to design the circuit, align the components, and solder it all together. Lastly, the control algorithm, the brain of the robot. We started off with a simulation in MATLAB, which helped us determine the size, weight of the robot, and then how much torque it required to move. After that, we started working on the motion plan. And then once the robot was fully assembled, we tuned the parameters rigorously until the robot could walk with a consistent compass gait.
So, why is our project unique? Walking acrobats are a common research topic in theoretical papers. There have also been previous attempts in actually building walking acrobats, but of course, they face their own limitations. They were only able to walk in downhill surfaces, or they were overly complex and expensive. Among a handful of acrobats, our Acrobot stands out for its simplicity and novelty. It prioritizes simplicity without sacrificing functionality. With just one actuated joint and minimal components, our Acrobot achieves effective locomotion.
How exactly does a robot walk? Let's take a look at this image right here to see all different phases of walking for the robot. So to begin, the robot initially begins stationary in step 1, and we then give it its first push, the external momentum. And the inclination angle is continuously measured, and once it hits a certain threshold, which we call theta I, the swing begins. Next, in step 2, when the swing begins, first before the actual swing takes place, we retract the swing foot solenoid to allow the leg to pass through without scuffing the ground, and then initiate the swing. So in step 3, during the swing, the internal angle between the robot's legs is continuously pulled and measured, and once it hits another threshold, which we call theta R, it reactivates the solenoid for impact, which next brings us to step 4, which is essentially waiting for impact. Once impact is detected from our robot, we move on to the next step, which is step 5, which is when the swing leg and the stance leg swaps from the controller's perspective, and this cycle continues. So in order to properly control a robot and have an adequate motion plan, we need to have controller feedback from all of the robot's angles. So in our scenario, it's Q1 and Q2. Q1 being the inclination angle and Q2 being the angle between the robot's legs. So in practice, how we actually measure these angles, beginning with Q1, we use time-of-flight sensors. Time-of-flight sensors are essentially an infrared laser which shoots a signal at the ground, wait for the signal to return to the sensor, and when it receives that signal, based on the elapsed time, it gives us the distance. So using these sensors, we used a polynomial regression, which we just took a bunch of data points and then measured them using this method. So that's how we measured Q1. So with Q2, the angle between the robot's legs, we actually had to make modifications to our servo motor. Our server didn't come out of the box with an analog feedback, so we had to actually open it up, solder on a new wire to its potentiometer, which allowed us to access a voltage for every angle, and with this, we got the angle Q2.
The Walking Acrobot is a robot that helps us understand how humans walk. It's used in research to learn more about movements and in medicine to help people recover from injuries. By copying the way people move, it can also help design better artificial limbs. This technology is changing how we improve walking and mobility for many people.
So to summarize, our team embarked on a design-driven Capstone project focused on creating the Walking Acrobot. Our process unfolded through numerous iterations, beginning with conceptual designs on paper and progressively evolving through hands-on experimentation and refinement. Along this path, we encountered a myriad of challenges that tested our resolve and ingenuity, but each obstacle required us to revisit our designs and strategies, and with every setback, we gained valuable insights and knowledge. This iterative process was not merely about solving the problems, but about understanding the intricacies of power, angles, and mechanics that, across all the parts and components, it eventually gave life to our robot. So our commitment to rigorous testing and continuous learning allowed us to refine each subcomponent, slowly but surely, enhancing the robot's capability to walk with autonomy that seemed very distant at the onset of our project. The countless redesigns and adjustments, while daunting, were steps on our path to realize our ultimate goal. So now, as we present the final design of our Walking Acrobot, we reflect on a journey marked by perseverance, teamwork, and our relentless pursuit of knowledge. Thank you for joining us in this presentation, and now let's turn our attention to the fruit of our labor, the Walking Acrobot in action.
Go get her!
Go!
Get up, Fran. Go!
I'm not gonna make it!
Yes, you are. Yes, you are. Come on, Case has it. Get back here, Doyle.